All right, this video is 6-7, modeling real world data with sinusoidal functions. Sinusoidal functions are, here it is. Any function can be written as a sine or a cosine function. Phase shifts will vary. To avoid a greater than necessary shift, use sine if the function is around 0 at x equals 0, or cosine if the function is about the max or min at x equals 0. So that's how you pick which function you should be using. All right. So an example on page 37. Open that up and read that. It says the table contains the times that the sun rises and sets on the 15th of every month in Brownsville, Texas. Okay. On our page here, it says let T represent January 15th, T1 equal January 15th, T2 equal February 15th, T3 equals March 15th. Okay. So the first thing it wants us to do is it wants us to write a function that models the amount of daylight. In order to write that function that models the amount of daylight, I actually do need a chart that applies and helps you know how many hours of daylight you indeed do have. Okay. So I'm going to write down that chart there. I'm going to start with my month, and on the bottom it's going to be hours of daylight. Okay, so month 1, okay, I can subtract those hours to figure that out, but that's going to equal 10.68. Number 2 is 11.3. Number 3 is 11.98. Number 4, 12.77. 5 is 13.42. 6, 13.75. 7, to carry my table out, 13.6. 8, 13.05. 9, 12.3. 10, 11.57. 11, 10.88. And then 12 over here is 10.53. All right, so these are the values here for this. If I'm going to create a function here, I can take these values and I could write my own equation for them. I totally could do that. Or I could put them into my calculator. And so I'm going to do that. So I'm going to go to table. So that's second table. And I'm going to put those values in. So like, wait a second. No, I don't want to put them in table. I want to put them in stat and edit. And I'm going to put those in. So list 1, I'm going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then over here on the right side, I'm going to put in all those values. So 10.68, 11.3, 11.98, 12.77, 13.75, 13.6, 13.05, 12.3, 11.57, 10.88, 10.53. All right, so my numbers here are from 1 to 12 on my window. So I'm gonna go my X-Men, I'll go from 0 to 15 by ones. My Y's are gonna go from like just below 10 to, so I'll say like 10 to 14, so it fits within there, scale of 1. And let's make a graph, and I'll see my graph right here. Okay, so it's looking kind of like a trig function for me. If I go to calc, nope, I'm gonna go to stat, and I'm gonna go to calc in there, and this thing looked like a sinusoidal regression. So I'm going to push sin reg, and I'm going to push calculate, and it is going to calculate for me my A, B, C, and D to use to make a graphing calculator model here. All right, so I'm going to write this function with, it has a sign, and I'm going to write it out, we'll say to 1 decimal. So right here, it's going to be y equals 1.6 sine of b, so that'd be a half, so that would be 0.5 theta minus 1.6, that's actually normally a minus, so I'm going to make that a plus, and then plus 12.1. And there you go. There is the equation for this sinusoidal function. Okay. Now it's going to ask me down here. Okay, we did on a calculator instead of checking. Use your model to estimate the number of hours of daylight on September 30th. Well, we know that the number of daylight hours, okay, for September 30th, well, we know September was 9. These amounts are at the 15th of the month, so the 30th would be halfway through our month here. So September 30th would be equal to 9.5. So we are going to plug in 9.5 where our theta is right here. That theta is representing our time, so we could have put that in as a time in our graph there. So I'm going to take this, and instead of a theta, I'm going to put in 9.5 and see what that comes out to. I'm going to actually put it in here, see what it says. Make sure my mode is correct, since I don't know where this calculator came from. 1.6 sine of 0.5 times 9.5 plus 1.6 plus 12.1, and that comes out with 12.2. Okay, it looks like in the book the answer comes out to 11.95. Probably because I rounded to 1 decimal and they rounded to 2 decimals, which shows the importance of rounding and being careful with our rounding. But that comes up to 12.2 hours of daylight. All right, one more for you, taking a look at how this one would look. It says, an average seated adult breathes in and out every 4 seconds. The average minimum amount of air in the lungs is 0.08 liters, and the average maximum amount of air in the lungs is 0.82 liters. Suppose the lungs have a minimum amount of air at t equals 0, where t equals time in seconds. Write a function that models the amount of air that is in our lungs. Okay. Let's look at what that would look like now if we were to actually solve this, okay, by hand and not just on a table. So this gives me some really important information. Let's take a look at it. First, let's start with our function that we would use. Thinking about this, it says, suppose the lungs have a minimum amount of air at t equals 0, minimum. Which function would show us a minimum? Okay, that would be a negative cosine. So that is the equation we are going to use here. A negative cosine to tell us, and this is the one I'm going to use, kt plus h. Okay, because I'm not going to have any sort of shift, because I know that my minimum happens at t equals 0. So now I need to find my a, my k, and my h. That k is impacting my period of time this happens in. All right, so my a, it tells me the max amount of air is 0.82. That's my max. And my min is this, so this is max, and this is my min. Okay, so in order to find my amplitude, I'm gonna go my max minus my min divided by 2, and that's gonna tell me the midpoint between those two things. Okay. So that's going to equal 0.37. All right. Remember up here that this is A, so when we plug it in, that 0.37 will end up being A. All right. So now my H, right? This tells me where my midline is going to sit, and how we find that is we need to find the average of these two, so we need to add them together and divide by 2, and that'll tell me what the average location between the two spots are, and that's going to be my midline, so that'll be my H value. Okay, so this is how much is between them to know my amplitude between them, and then we got to divide that by 2. This is the actual average, or the midpoint between the two max and mins. And then the last thing I need to find is my K. Okay, my K is going to be related to that period, which is our 2 pi over K. And up here it tells us that an average adult breathes in and out every 4 seconds. So that is going to be the period of time in which this happened. So that period is 4, and now we need to solve for that K. So I'm going to go 2 pi divided by 4, or K is going to equal pi over 2. So now I have all the pieces I need to plug into my equation here. So I have a negative A, 0.37, cosine, my K is pi over 2t plus 0.45. I know there is not a parenthesis and a C on here because I know there's not going to be a phase shift. I know there's not a phase shift because it tells me that my minimum amount happens at t equals 0, and I know that there is no shift there then. Okay. I could then take that and graph that on my calculator and see what that rhythm of breathing looks like. Okay. And then the last thing it asks us to do is determine the amount of air in the lungs at 5.5 seconds. Okay. So how we are going to do that is we have a t of 5.5 seconds. I have a t up here in my equation, and I'm going to plug that in. and I'm going to throw out my calculator and I'm going to solve, and it's going to tell me exactly how much air is in my lungs. Cosine of pi over 2 times 5.5. That all needs to go in my cosine. I'm going to throw that in my calculator, and that's going to get me an answer of 0.71 liters at 5.5 seconds. Okay. This information can be used to figure out how much liter is in someone's lungs as they're breathing, to find out if they're getting enough and what their lung capacity is, etc. So that's kind of the application here with those trig functions.